So I've changed the title a little bit, but the content's the same. I'm co-opting this and adapting this Gauguin quote. Where do LLMs come from? What are they and where are they going? I'm not going to answer any of these questions in any sort of like exhaustive manner, but hopefully, especially if you're not a domain expert or haven't been working with LLMs directly, you'll leave this with a bit more of an intuition about the state of the field and some of the reasons to be excited about things going forward and how you can contribute even if you're not working in machine learning directly. So I can probably gloss through the early slides early on, but generative AI, especially in language, has entered the age of application. We've seen so many examples today, from medicine to robotics, via obviously being able to converse with systems that can give you access to information like Google Bard or ChatGPT. We're reaching a point where this is commercializable, or where there are applications that often sort of exceed the design intent of the designers, right? Like people are using this technology in ways that we don't anticipate, and that's a magical moment in any sort of class of technology. And this, again, echoing something that was said in the opening remarks, is a fourth step in this sort of like decade, 12 to 13-year period sort of pattern of innovation, starting in the 80s, where we saw the advent of personal computing, putting general-purpose computers in every home rather than being in the confines of academic labs and industry. With the advent of the World Wide Web, we then in every home had access to information on a global scale in real time from every desk, or everyone who had access to a computer, which I recognize was not everyone. In 2007, as pointed out earlier, we entered the era of ubiquitous computing. I mean, smartphones existed before in some form, but really this was like the go-to-market moment for this class of technology, where we had these general-purpose computation, communication, and information access devices in our pockets, which we're now obsessed with, and that's both good and bad. And now we're entering, I feel, this new era where we have a new class of technology which provides us access to knowledge, to external information, and eventually, or actually in today's world, to tools that can operate on this knowledge and perhaps create new knowledge or interface and act on our information through a conversational interface or through other modalities. So what is powering this significant change, this sort of like inflection point in the history of our technology, or yet another inflection point? Well, this is the only bit of math I'm going to have in this talk, and I'm really only including it to illustrate how simple the core idea behind this technology is. And this starts with a very simple formula, which is that the joint probability of a string of text, but as was pointed out in the talk earlier, it is in fact any sort of sequence of data. This decomposes according to the laws of probability into the product of the next item in that string given everything that's come before. So if you take the product of all those probabilities and like move that window across your sequence, that right-hand term is equivalent to the left-hand term. And that right-hand term is in practice what we seek to approximate with various sort of machine learning techniques, especially neural networks these days. And that's nice for two reasons. First, it simplifies and factorizes the problem neatly in a way where we can exploit dynamic programming or reuse computation, but also because it's something that you can generate from. You can sort of, say, by generating the next element in the sequence and then passing it into the prefix and then iterating over this, we can produce novel sequences and sample from this distribution. And that can be used for things. And to move away from mathematics, I'll just illustrate this with this nice little idea of like, the neural network parameters or whatever the function whatever the model you're using is inside this green box, because it seems so much more friendly than the term black box. And it's mapping some sequence to the continuation or what comes next, what comes after that sequence. So some applications of this obviously fit into the language modeling paradigm, which, as pointed out, is something we've used for historical reasons, but where you have the text you've generated thus far, and then you can have a distribution over what comes next and continue that. And everything from the autocomplete we've had in our phones for about 2 decades to being able to do copywriting fit this sort of paradigm. But it also, other sort of mappings that we see more as transductions or transformations also fit this paradigm, such as translation. And that's just a matter of sort of formatting your data in a way where you really only care about part of your modeling problem. You don't optimize across the entire sequence. But the same sort of objective can be used to train a model that will translate English to French, French to Chinese, and vice versa. And thinking more generally, this is actually just a general model of computation. So you can sort of see this idea of mapping, at least within the realm of sequences, but eventually other modalities, instructions plus data to the completion or execution of the instructions on the data as fitting this exact pattern, as long as you can express the execution trace as a sequence. So this idea of this factorization of probability has been known for way more than decades, and we've been thinking about large language models and sequence-to-sequence models for definitely the last decade with neural networks and far before with other methods. So why is the large language modeling revolution happening now rather than in the past? And there are several ways of looking at this, but the main reason, I think, is that the field has somehow settled on a single architecture for processing text and sequences at this particular point and come up with a good bag of tricks for training this architecture. And previously, between 2010 and 2018 or 19, we were all occupied with publishing NeurIPS papers on overly complex new methods, and as was pointed out in Jonathan's talk, not properly optimizing the baselines, and often those results didn't stand up to proper ablation studies. So now we're less obsessed with that, and we're more interested with doing something different, which is scaling things. And that's because while we all recognize that the transformer isn't perfect, and that is probably not the last word in neural networks, at this particular point, the commercial and practical benefits of doing things with it outweigh the benefits of really thinking about replacing it tomorrow, right? Obviously, there's fantastic research that is focusing on just that question. We're not a monolithic field, but a lot of people are focusing more on the application now. So we sort of iterated towards this position where it's more about scale. Fundamentally, why this architecture is successful is because it scales very well to our hardware. So we know that from Hennigan and al. And some related work from 2020 that scaling model size improves final performance across a large range of tasks, be it image recognition, text-to-image transduction, or image-to-text transduction, language modeling, video understanding, and mathematical problem solving. We also know that from Hoffman et al. In 2022, and this I think was an intuition that people had far before, the scaling the data set relative to the model size improves final performance, and as was pointed out in one of the previous talks, if you don't do that comparatively for your baselines, then you're producing a false comparison, and people still fall foul of that in 2023, so that's always depressing. But we know that if you feed more data to these large enough models, that you get these sort of continual returns, which is astounding. But that's not really where I think a lot of the that's exciting. It's exciting that we reach the point where you can just crank a lever. But you start to see diminishing returns, or at least practical returns due to the cost when the models get very large and you can't just train them ad infinitum. So there's other areas where we're seeing significant contributions to this strong shift in the performance of this class of models. And that's to do with what we're training them on. So again, this is probably bread and butter for a lot of people in this room, but I'll go through it for the sake of completeness. There's two kind of phases in how we train large language models: the foundation modeling stage and the fine-tuning stage. And so the foundation modeling stage is, as was pointed out earlier, the expensive and long stage where we train it from scratch over web text, programming, multiple languages, code, whatever modalities we really care about, getting into the model. And you can sort of imagine that the stage of training is where the model learns something about the syntax and, in some shallow sense, the semantics of the languages, or other sort of forms of sequence data that are present in the pre-training data. So it's important to reason about what sort of data you want at that stage in order to reflect it in the downstream understanding of the model. And we know from some publications, for example, from Petroni et al. In 2021, that these large language models trained at this stage act as soft knowledge bases, so you can query them for facts that are directly expressed or softly inferable from the data that they're trained on, but obviously it's sensitive to the time that data the facts as reflected in the training data. So if the world moves on and you haven't retrained your model in a year, then obviously it's not reflecting actual facts anymore. So the end product of this stage is that you have these large models that act as a foundation, hence the term foundation model, for a very data-efficient downstream task-specific learning phase. So that's really the important outcome here, is beyond just the knowledge of the syntax and semantics of the sequences, or some aspect of the semantics of the sequences that they're trained on, you have a model that learns very quickly on follow-on data. And I won't go into the details of why I think that's the case. So the fine-tuning phase is the cheap, fast, and iterative phase. It's cheap and fast because you usually do it. You train your model in the space of a day or two, sometimes a couple of hours. You do it on relatively few data. You do it on a single epoch. And it's iterative because it's cheap and because it's fast. You can sort of hypothesize that some data is going to help you on your downstream tasks. You measure extrinsically whether that adds utility, and if it didn't, you throw away your model and you start from the foundation model again. You don't retrain from scratch, right? And this is the stage where these models acquire specialist task-specific knowledge. And I think, around 2021, 2022, when we started talking about foundation models, we just sort of pictured this as being where everyone would do all the work and just do a bunch of different derivative downstream models, one for machine translation, one for semantic parsing, and whatnot. But it turns out that downstream tasks, the notion of what the downstream task is, can be very open-ended and sophisticated. So an OpenAI, it's only like about a year and a bit ago, produced the InstructGPT paper, where they showcased that by fine-tuning models on a more natural way of executing instructions, namely following instructions as we humans use to instruct one another and instruct ourselves, that we could get them to sort of act in a sort of very massive multitask setting. They're capable of solving a large range of tasks, extrapolate to new instructions, sometimes instructions which characterize completely new tasks that weren't really exactly specified in the training data. And separately, we saw around the same time, in fact, maybe a few months earlier, this paper by Thapilin and al., the Lambda paper, which is, I guess, the precursor to Google's Bard, where they showed, again, that with very few fine-tuning data, a foundation model could be nudged towards acting like an open-ended conversation agent, and this really baffled me at the time and still baffles me. It could act on tools. It could call into search engines or calculators and incorporate the results of the search or of the calculation into its output, sometimes even calling upon the tool latently several times. And that was the first sort of evidence that the data efficiency of these models permitted this agentic view, that we could treat these large language models as almost as agents in their own right, having sort of semblance of autonomy. And that was a very exciting moment in our field. So that sounds very exciting. So what's working right now in this sort of paradigm? What doesn't, and what do answering these questions at least partially tell us about what to expect next in our field? I don't have a timer up, so I don't know how I'm doing for time. So someone's going to wave at me when I have 5 minutes left, if you can. So there's clearly something special about this instruction tuning, this instruction following fine-tuning phase. So this is the results from Stanford's holistic evaluation of language models, benchmark of benchmarks. So it's a prestigious benchmarking exercise. As was pointed, at least in one of the talks today, take benchmarks with a grain of salt because they're probably in the pre-training data, and it's very difficult to verify that robustly. But what's very interesting here is that all the top models in this benchmark were the instruction tune ones, right? And they form a significant performance gap with in many cases, we have the corresponding model without the instruction tuning data, at least for coheres, and I think for maybe for AI 21 and Anthropics. For one of the OpenAI ones. So we have a good counterfactual of what the model would perform like without the fine-tuning data, and the performance gap is significant. And on top of that, even though we can't verify that the benchmark data leakage is happening in the foundation model stage, it definitely is, that isn't what explains that performance difference, because we can verify that that data isn't in the relatively small amount of fine-tuning data that yields this instruction-following behavior. So a relatively small part of the training data over the entire history of the model across the two phases is accounting for the significant jump in the final performance. So let's try and unpack that a bit more. What could be happening there? Well, we need to find ways of probing what sort of capabilities this instruction tuning phase yields in our models, and then eventually, I'm not going to do that today, aim to explain it. And so one of the questions we've been asking ourselves is, does instruction fine-tuning bring about some sort of deeper capabilities in line with how humans use language? So let's turn to philosophy. The Austrian philosopher Wittgenstein in his later work tells us that there's more to language than propositional content, than just stating what's true or false about the world. There's also all these aspects that relate to integrating how we use language within our society, within our communities, within our way of life, the pragmatics of language. We can't disentangle semantics from pragmatics. So can LLMs grasp pragmatics? If we ask GPT-3 in 2022, which we did, have you seen my phone? It answered, yes, I have seen your phone. And so that's a reasonable answer in the sense that it's on topic, it's consistent, it's not completely insane. But as a human, if you ask someone, have you seen your phone, and you just get that, and that's the end of the conversation, something's missing there, right? You're that's not quite getting at the question. So to qualify what's missing there, let's talk a little bit about the notion of conversational implicature, a concept introduced by Paul Grice in the 50s. Let's take this conversation. Person A asks, can I borrow your stapler? And person B says, my office is unlocked until I leave at 4 p.m. what does person B mean here? Well, they mean, and stop me if you disagree. Well, don't, because we don't have that much time, but I think we'd all agree that these propositions make sense in relation to person B's intent, that the stapler is in their office, that person A has their permission to borrow the stapler, that person B expects person A to help themselves, they're not going to do it for them, and finally, that person A probably should get their skates on and do it before 4 p.m. And none of these meanings is logically implied in the sort of mathematical logic sense from what person B said. They're implicated rather than implied. And we humans use this pragmatic mechanism a lot in conversation for expediency, efficiency. Underspecification isn't a bug, it's a feature of language. And we exploit that. We incorporate contextual and practical knowledge into how we communicate in order to resolve more propositions than what is said prima facie in most of our communication. So with my students Laura Rees and Akbir Khan and colleagues, we turned a simple version of conversational implicature resolution, binary conversational implicature, where the implicated proposition, or the main one, is yes or no, into a task. We had a bunch of scenarios that were collected from a psychology data set, where one participant asks a question or says something, another participant says a response, and then we have which means yes and which means no. We measured the probability of yes and no conditionally on the story for large language models, and then we stack rank according to that probability, which gives you a binary classifier for free. If you don't have access to the probabilities from the API, as we didn't for GPT-4 or for ChatGPT at the time, you can do a Monte Carlo estimate. And what we notice here is that there's two categories, right? There's the models that metaphorically don't know how to get the stapler, that don't understand implicature better than random, and ones that do understand implicature close to human performance. The ones that don't are all foundation models, so the models that are just trained on general text. We notice that more training data doesn't change the result at all, and making the model larger doesn't change the result at all. Also, surprisingly, multitask models that have few tasks but a lot of data per task, like FLAN T5, don't perform well here either. That I'm still struggling to understand why not, but hey. The models that do know how to get the stapler metaphorically are the instruction-tuned models, the ones that are trained for a very small part of their overall lifetime on this sort of massive multitask setting. Something about that, which is not, most of those tasks, or very few of those tasks, do anything that is explicitly about resolving implicature, if at all, but they somehow get some aspect of pragmatics from that stage of training. And again, that's astounding, that this capability, it's a very simple form of pragmatics that, we'd love to probe more complex forms in follow-on work, but that sort of like dividing capability between foundation models and instruction-tuned models comes from a very small amount of the data, which doesn't in itself directly reflect the task that we're looking at. So I'm going to finish ahead of time because I've been able to gloss the beginning of this presentation so much, but let's try and think a little bit about what might be next from the observations that I've made so far. And the first is, again, like echoing points that were made in a number of talks today. We're only beginning to scratch the surface now of how people, businesses, not organizations that aren't business focused, and also are going to leverage the power of models that can transform how we access and act upon information and eventually produce it, or actually produce it right now because we can produce AI art and music and whatnot. That's really what's so exciting about this domain right now is, unlike what we were doing in machine learning, even 5 years ago where we had these use cases and we were delighted that the same kind of neural network could solve several use cases if you trained it on different data for each of them. Now, we're producing models that are surprisingly general purpose, and we don't anticipate the ways in which people are going to mess with them. And finding that out is part of the delightful discovery. We're also only beginning to scratch the surface of why these models develop these capabilities and are so surprisingly creative and robust off very few data, sometimes not reflecting the sort of tasks that the downstream users call upon them for. And it just seems that, okay, when they fail, we just find out how they fail, we collect more data, and we retrain them in that sort of like fast iterative stage, and it keeps on improving. And we don't know how far that paradigm goes. You don't know if that's going to get us all the way to human performance as we keep on cranking the sort of flywheel that Angela illustrated so well in her talk with collecting preferences and doing RLHF, or whether that's at some point going to hit a brick wall, and then we'll have to have a substantial paradigm shift to get us beyond that. And that, in part, is because we're only starting this sort of phase of co-adaptation with downstream users where the complexity of things they're doing with these systems is evolving with their experience of what they can do so far. And these two questions are not orthogonal or separate. Downstream application and research are not two completely separate worlds. We're really at this stage where these, more than ever, operate hand in hand. Research has to rely upon experience of the failure modes in the wild and of the diversity of downstream use cases where the model succeeds in order to understand where the research boundary is and where we can next make the most progress. And in turn, when we make that progress, often at an astounding pace these days, that unlocks new capabilities, new possibilities for downstream applications that industrial research and other communities and individuals can use in terms of downstream use. So if you want to help us solve AI, whatever your background is and however you want to approach this, the best thing you can do is go forth and build something with it. And I hope that this final talk will be a good sort of point to land on in terms of encouraging people to do just that. Thank you very much for listening.
All right, thank you so much for that tremendous final chapter on this day of talks. A great note to end on. Do we have any questions for Ed from the audience? Oh, question right here.
So for situations where the experimentation is in a high-risk area, such as healthcare, what would be your suggestion for doing the 3 things you had on your last slide?
Yeah, so that's obviously something that there's a tough methodological nut to crack that applies both there and obviously with the sort of products that we are interested in Alphabet, where we obviously it might not have the same sort of degree of danger of getting a medical prognosis or diagnosis wrong. But we deal with private information, and we value, obviously, our customers' trust in us. And so we can't just directly experiment in the wild like a startup does, which is, a shame in terms of being able to move fast, but it's the responsibility you have by being a large company. So the short answer is, I don't know. The long answer is that itself is a research question. Can we find suitable proxies or safe proxies for sensitive data where it's not harmful? And so obviously you can get data that's simulated, or you can use real data but produce derivative or augmented versions of this data, train on that, and see if that significantly bootstraps the capabilities of the model to the point where it could be deployed. Once models have sufficient capability, we can deploy them with humans in the loop in terms of validation. So I remember years ago when Microsoft was experimenting with, pre-OpenAI with MST, right? And they were having a model that was, I don't actually remember the technical details of the model, but effectively was, constantly training off user interactions with it. Obviously, people from the internet decided to get it to say a bunch of toxic stuff, and that was an embarrassing moment. That could have been avoided if, while they were experimenting with that, they had a human just check every tweet before it tweeted and said, maybe not this one. Now, in the context of a medical application, in fact, in the context of a number of applications, it's interesting to think about, can we deploy these in a way where we require human validation in order to do that, where it provides, its opinion about what a diagnosis or prognosis should be in a medical context, but a surgeon or, you can tell I'm not a real doctor because I don't know the proper vocabulary, where a specialist looks over it and makes the final call. And those situations are very interesting because, first of all, if the failure mode of the automatic system complements the sort of the typical failure modes of humans, then it's the intersection of both of those failure modes that you get as part of the whole system if both have to make a joint decision. But on top of that, by having a human in the loop as part of the normal operation of the hybrid system making the final decision, you get signal for free about how to then further improve the system. So exploring this whole space of how we can safely deploy these, either by having humans act in symbiosis with the system rather than just go straight for full autonomy, or how we can get proxy application scenarios or data collection scenarios that don't have the harmful characteristics. Those things all have to be explored in order for us to be able to build safe and sort of privacy-preserving products with this. But that's not a solved problem, which is why it's exciting.
Oh, there's a hand up there.
I'll let you pick the questions. I can't barely see here.
Thank you very much for the very interesting presentation. I have one question. I mean, what you discuss about the role of instruction following fine-tuning is quite interesting. On the fact that it seems that models which were trained with instruction following, this seems to are set apart from other models from some tasks. Now, my question is, do you have a intuition of understanding if they, the fact that they are apart comes from the way we evaluate them, or if they are fundamentally different, if they gain really competencies that are different from the foundational models?
That's an interesting and deep question. I mean, so first, I'll answer in two ways. So first, in terms of it's clear that it's that class of models that the general public has had a difference in qualitative experience with. So when ChatGPT came out, the main contribution of ChatGPT was a UX difference. I mean, the performances are very similar to DaVinci 3 models. It's just that an average person doesn't know what an API is. I don't think so. I hope that's not a judgmental thing to say, but I didn't know what an API was even 10 years ago, and would not go out of their way to just call upon something called DaVinci by a company called OpenAI without having just experimentally. And then when you're dropping them into a way of interacting with this system that is natural, through an interface that people use to talk to other humans, then there's not that barrier to entry. And people, when they had access to something like DaVinci 3 with a little bit of conversational magic thrown on top, found this astounding. It was unlike anything that they had tried before. I mean, obviously they could have tried Lambda if we had released it, but but that's the point. It's the fact that you have something that can just answer arbitrary questions, seemingly compute instructions on text, because it didn't have the extensions at that point, was magical to many people. And I think so. There's something qualitatively transformative about being able to solve seemingly arbitrary tasks. Now, about evaluation, that brings up a question that I think a point that was made in several talks, and I was talking about this separately with a number of the other speakers. We obviously need better and new ways of evaluating these things. It's clear that there's a significant risk of data set poisoning, and that results like passes the bar exam and all that, there's no reason to put any strong credence to this. And when we do know that when we take these general purpose models and evaluate them on specialized domains such as medical domains where the data is unlikely because it's significantly PII or highly sensitive data, that they need further training, right? So there needs to be a revolution in rigor with regard to how we evaluate these models that's entirely due to the scale in which we train them, to the fact that they're ingesting the entire web and that data is likely to be out there. And again, that's as much a practical need as it is a research question, and it's one we need to solve if we want to make progress we can trust with this class of technology.
Thank you.
There's a question over there, I think.
Hi, thanks a lot for the presentation. At the beginning, you mentioned the fact that one of the reasons why we are in the fourth wave of the IT revolution, let's say, is because we settled on a model. And I think this is an interesting point, and I was thinking about the fact that there are many components that led to ChatGPT. So not only the model, but the fact that now there is a technological infrastructure that allows us to have big models, also the data that we give as an input, the method itself, so reinforcement learning from human feedback, which is a sort of revolution. So do you think it's really the model that...
No, I mean, okay, that was... I hopefully stated that and didn't forget to say, but that was oversimplifying. I mean, the fact that it's the model with the fact that we have powerful accelerators, and that kind of model scales to those accelerators for training and distributed training significantly better than recurrent neural networks did. It's the availability of an increasingly diverse set of data. It's good optimizers. I mean, the point we are in history is very much standing on the shoulders of the giants of the last few decades of our field. So it's not just Transformers came along, but the fact that we've settled on Transformers as the sequence processing architecture, and increasingly for vision in other domains, is a significant shift from the sort of work that was happening in this field over the last decade, where everyone was doing LSTM++, coming up with different models of attention, and that's fascinating, and that work is valuable, and perhaps we'll see the value of that work resurge, come back up as we perhaps hit a brick wall with this architecture. Who knows? But we have concentrated our energy on thinking about data, scale, and evaluation, and downstream applications significantly more than sort of neural architecture hacking. And yeah, we're seeing the dividends from that. So that's just that's a byproduct of the maturity of our field and all these different axes, rather than just it was transformers all along that done it, right? It's like that's clearly not the only part of the success story.